modeled using a DIgSILENT PowerFactory. In the previous session, we have seen how differential relay works. In the DIgSILENT PowerFactory portal, there was an instruction how to model a differential line protection. However, there is no information how the input parameters are inserted, short circuit fault currents and relay setting values are calculated, and how basically assumptions are taken into account. So in this video, in this video, we'll go through them step by step. So here is the DIgSILENT model prepared, for example, in here. So what we need to know is the input parameter. The input parameters are, for example, the grid infeed, such as fault level, the busbar voltage, which is 132 kilovolt in this case, and transmission line parameters, such as positive and negative zero sequence impedance values. And then, of course, the line length is 50 kilometer as an assumption. And then assume the load power, which is adjustable, depending on the power factor, is 100 MVA divided by square root 3 times 160 kV, which is 437 load current or nominal current, or 0.437 kiloamp. Well, this 437 amp is during a healthy, the current flow from a generator to the load, basically amp the load current. And here is the relay configuration. And on the relay configuration, the CT ratios are 1200 to 1 amp. So if the CT ratios are, the CTs are installed at both ends. So the primary current is 1200 amp, and the secondary relay current will be 1 amp. The type of relay is 87 or line differential. So the way we should model as a data input is generator, transmission line, bus, and load. For example, on the generator side, we have to insert the power flow or the load flow the generator load flow information, and the fault infeed or short circuit. Transmission line, as what we said already, line lengths and parameters or impedances, as you can see. And then the bus is about the voltage, and the load is about the load power. Okay. For example, if I have to show you on the model, this is just what we're talking about is here. Generator is load flow is here, information in here, and load flow is short circuit is here, fault level. And for transmission line, it is parameters are here, and this is the line length. So if we click in here, we can basically update the basic data input in here. Okay, and then the load flow is also in here. After that, what we need to do is to do load flow to ensure that the network works correctly. So now, if you can see here, the load current is flowing from generator to the load. Okay, so when we ensure that the load flow is correctly modeled, then we can install a relay. Well, what are the steps? Let's have a look. So first of all, we need to define what kind of relay type and the CT ratio, and of course the theory behind. So we need to understand how do we calculate differential current, restraint current, or base current, pickup current, and a slope. Okay, For example, in here, as you can see, the setting pickup current in the setting, the pickup current is 0.45 amp secondary, which considers 20 to 30% above full load current, where the full load current is 0.36 amp. Well, we need to explain how. For example, as you can see, the load current is 437 amp, the load current during the nominal or the healthy. And then if we divide by the CT ratio on the primary, which is 1200, then we get the load current, secondary current is 0.364 amp. So this is what we call is the ratio between when we convert from primary to secondary current. Okay, so this is the maximum relay or the maximum current the relay can see under normal load current. So to consider a safety margin, we can just increase this one 20 to 30%. So to avoid any false tripping, for instance, or CT ratio or CT errors. So we can set the pickup current to be 120% times the load current, the maximum load current, which is this one. So if we multiply by 1.2, which we'll get 0.437 amp. Okay, so we can choose slightly higher, 0.45. So this is the pickup current is 0.45. What does this mean is if a fault happens, the relay needs to pick up this fault. The fault at 0.45 amp, basically. So if that's the case, then how do we calculate the fault impedance? How do we calculate the fault current? Well, if you can see here, we need to first calculate the source and line fault impedances. So I said we need to divide to calculate the source impedance, which is the impedance of the generator, V square over S base, okay, or sorry, V square voltage square divided by the fault level, basically. So we get 1.9, and we can also calculate from Z line to the fault point, which is because the fault point is at 50% of the line, which is the total is 50 kilometer, and we just divide by 2, 25 kilometer times a positive impedance. We only calculating at the moment a three-phase fault. So 25 kilometer times the line impedance, the positive sequence impedance. So we'll get 22.8 impedance. That is from the impedance of the line to the fault point, basically. And then total impedance is from generator to the fault point is we add the source impedance with the line to fault impedance. So we'll get 24.7 ohm. So it is easy now to calculate the fault current, which is phase voltage divided by the total impedance, and then we get around 3 kiloamp or 3.1 kiloamp. As you can see, it is 3.1 kiloamp in here when we create fault in here. Well, how? Show you here. If I click in here, create a fault, 50% of the line. This is a complete method, three-phase fault. As you can see, it is 3.1. Obviously, we can change the fault point, and then of course the fault current magnitude will be changed. Or I can put 90% of the line. Of course, the fault point will be changed. We can calculate is just to multiply by the line lengths. Okay, so this is the fault impedance at fault current at 50% of the line. Okay, so now since we have fault current at 50% of the line, it is easy to understand fault current to secondary transmission line. So the load current is 437, in a primary, and then if we convert it to secondary, we already mentioned that it is 0.36 amp, and the fault current is now 3085 amp. And then if we convert into secondary current, which is 2.57 amp, well, you can see if we divide the for example, the fault current divided by the nominal current, you can tell the ratio. So you can tell that the fault current is much higher than the load current, basically. Or if you divide the secondary current, 2.57 divided by 0.36. Okay. So you can see when the fault, before the fault, it was 437, but after the fault, it is increased to 3000 amp. Okay. You can easily calculate the ratio, basically. So now we need to understand how this relay will trip when there is an internal fault and how it will behave for fault on the external. Okay. So now during the internal fault, we need to calculate in theory. So for example, the differential current is the difference of the currents, which is 2.57 minus 0. What it means is, if this is the line, and then if this is the fault, because the fault is coming through only one side, so the CT will only read 2.57 current to the fault point, but this CT will not read anything. Okay, so we just subtract the difference. The difference is now 2.57 amps, and then the bias current is, which is the average current, so we add this to 2.57 plus 0 divided by 2, which is 1.285 amps. Okay, so you're given a formula in here anyway, and we can apply the slope 20%. We'll talk later about this, why. So we can calculate the operating current of the relay, which is this one. This is the formula. So 0.45, which is the relay pickup current, we have already discussed it. We apply 20% above the maximum loading current, so plus 0.2, which is 20%, times this bias current. Okay, so we got a relay operating current is 0.7 amp or 0.71 amp. So since the fault or the differential current, which is 2.57, is greater than the relay operating current, the relay will trip. Or this is a setting relay, basically. So since the fault current, the differential current is higher than the setting current, the relay will trip. Yeah. So this is for internal fault, when there is internal fault. Yeah. For external fault, again, the relay will see let me just erase this one. Assume the CTs are here, and a fault is here, where the relay is here. Okay. So now this fault current is outside the box. So this CT will read the same current because we have only source in that side. So all the way the current will move. So the current read by this CT and by this CT will be the same, which is 2.5 average. Say 2.5. We can just maybe sometimes this CT, because it is receiving high amount of fault current, it can saturate. So let's have I1, which is this one, 2.5, and then I2, which is on that level 2.48. So the differential current, the difference between the two current is 0.02. This could be due to CT error. Okay, so the bias current is the average current, so 2.5 plus 2.48 divided by 2, which is 2.49. So on the slope, because this is for external fault, we can increase the slope. Since we can use 1.5. So we need to calculate the operating current. So operating current is equals to, which is this one, pickup current plus the S times I base. S is the slope in decimal. So 0.45, the pickup current, plus 0.4 times 2.49, the bias current, which will give us 1.45 amp. So this is now the relay setting. Since the differential current, which is only 0.02, is less than the relay setting, the relay will remain stable or no trip. Well, this is our plot. So this region is trip region. So in this region, the relay will trip for internal fault. Okay, and then in this region, it is restraint region, or the relay should not trip. So the relay will remain restraint for external faults. Okay. So how do we then put this value into the relay? So let's have a summary of the values. So as you can see, so this is the minimum pickup relay, which is 0.45, and then this is the bias setting, which is 20% slope. The second slope is 40%. Okay, and then this 1.5 is between slope 1 and slope 2, which is around here, and this 20%, this 20, as you can see, this 20 per unit is when we have a maximum fault just from that. Okay, so now we can insert these values into the DIgSILENT, because as you can see here, this is the differential current, and this is the bias current, and this is how the slope is configured. So for example, this is slope base K1 or percentage, the 20%, and then this is the 40% a slope. Okay, and then this is where the K1. Okay, so now this is how we insert the values. So in the relay, we click on the differential, and then of course we put the value. The first is pickup relay 0.45, and then the next is the slope, of course 20%, 40% the slope, and this is the knee point 1.5, and then the next one knee point is 20. Okay, if I take you through to the DIgSILENT relay model. So this is the relay. So we click on the differential, we just plug in the values in here basically. Okay, that's what it means. After that, we assess the relay whether it can trip for internal fault or not, and then the same as for external fault. For example, as you can see, we create a fault on 50% of the line, the relay provides a trip. The fault is in here, as you can see, and then the trip time is 25 millisecond or 0.025 second. This 25 millisecond is typical relay trip time for differential, because up to 30 millisecond is expected if the relay provides. Okay, if there is an external fault in here, which is outside of the relay protection, then the relay should not trip. As you can see, it does not provide a trip. It only gives you 9999.999 second, which means the relay does not trip or remain stable. Okay, if I take you here again in the DIgSILENT, I have a fault in here, and then I can just show this one. Fault is in here, and the relay trip time is 0.025. Okay, and if I create fault on the bus bar, for example, the relay does not provide a trip 999. Okay, or if I just create a fault on this line, which is outside of this protected zone, the relay does not trip again fault. As you can see, it's just 9999. Okay, so what it means is the relay remains stable or does not provide a trip for fault outside this protected zone. But for when the fault was on the within the protected line, then the relay provide a trip. As you can see, we can move the fault location, say 10%, still trip, or 90%, up to 99%, it should trip. Okay, if I put 101, it does not allow. Maximum is at 100 trips. What does this mean? It means the relay protects only the line within the two bus bars. It doesn't protect. It doesn't trip for faults outside the protected zone. Okay. So the challenge comes. How about when there is in-feed faults in here? When the fault current is coming from both sides. Well, when it's the same principle basically. It's the same principle. The way we need to calculate the impedances, but the relay always remains stable for faults outside, but it trips when the fault is inside the box. Okay, so as you can see here, a couple of scenarios in here. We can create fault in here, fault in here, fault in here, fault in, fault in. As long as the relay sees the fault inside the zone, protected zone, then the relay trips. For example, let me just create a fault in. There are 4 scenarios. For example, if I create a fault in here, which is outside the box in here, the relay does not provide a trip. Regardless of the fault impedance, whether it comes from here and then in here, and then if as long as the fault is within the protected zone, just put 50%. Sorry, it has to be fault in here. Then the relay should provide. Oh, sorry. Now fault is okay because there is a fault magnitude increase, so we need to adjust the setting basically. For in here, as you can see, when a fault is in 50%, because of the impedance of the line is different, it's still in here. Show this one to this one. Well, the setting is different, but it provides a trip in time, if you can see here. Yeah, the characteristics are different because we have to adjust the setting because of the impedances. We haven't calculated for this one. We only calculate the impedance, fault impedance for this one. Okay, but it works. Okay, so basically the differential relay should provide tripping for internal faults and should remain for external faults. Well, if the above is not satisfied, the relay is mal-operated or it is providing a forced tripping, and a correct setting configuration is required. So correct setting needs to consider CT measurement errors and communication delay, as well as CT saturation, especially during through fault currents. So in the future, there will be a work done on differential protection of transformers, bus bars, generators, and how to improve protection stability, especially during external faults when CT saturation or measurement delay happens. So thanks for watching. See you later.